Right, login. Okay, logistic regression. So you see, three files. One is two are the practicals file, HTML format and PDF. So you can use either one. And dataset diabetes.dta. Okay. Um. So I'll be quick, because um I think you're quite familiar now with Rstudio Cloud. At the same time, if you want to use your Rstudio on your computer, that's also fine. Okay. Before we go on, if you have any questions, you can ask lah. Okay. Do you have any questions, burning questions at the moment before we continue? Logistic regression, and kita boleh buka, we can open up the HTML file or the PDF file. Okay. So PDF file, let me check. PDF. Okay lah, I download this one. So this is the PDF format. You have the short practicals and long practicals. Practicals is basically the most important codes or practicals that you have to do lah. Sorry. Okay. I'll send to you later, Irfan. Okay. And the long practicals are basically the more elaborate instructions on how to perform logistic regression in real analysis lah. Okay. For the exam purpose, you don't have to do all the exploratory data analysis or data wrangling lah. I think so. Exploratory data analysis, making plots and graphs, that one not necessary. Okay, for the exam. Okay, because we assume, or I assume, that you already master that part, right? Doing exploratory data analysis. Okay, so in exam, basically you just go straight to if linear, then linear, if logistic, then logistic regression. Okay, so in the short practicals, so basically as a statistician, we do estimation, inference, prediction, model checking. Okay, these are the four things we do. Okay, number one, estimation, which means we estimate the regression parameters. Two, inference, checking the p-value at the 95% confidence intervals. Prediction, making prediction. Okay, find the fitted value, and model checking, to check for the model assumption. Right. So next, the notes. Okay, the notes. All right. I think I missed the notes. Right. Okay. This is the practicals. The notes you don't have yet, I think, or maybe I accidentally deleted it last night. So let me let me upload the file again.
Prof.
Yep.
Irfan asking about the data.
Yeah. Tak apa. I've told Irfan. I'll send later. Okay, after that, you can write anything in the title. For example, logistic regression, practical. I choose HTML, click OK, and remove everything starting from line number 12. Okay, so first we prepare our data. Okay, um, so we prepare environment. I prefer to say prepare environment. Library tidyverse. Okay, and then we are going to use another 3 packages: Broom, Heaven, and Here. Maybe not necessary if you are using Rstudio Cloud library. Okay, right. What else? Okay, and then you can click this green button. Most probably it will say that you don't have the packages. Okay, so you say that there is no package called tidyverse. If I run library Broom, Control Enter, it will also say there is no package called Broom. If I Control Enter Heaven, same thing. And if I Control Enter, if I click Control and Enter a key on my keyboard for here, same thing. Okay, there is no package called here. So it means that we need to install these packages, right? So to do that, go to Packages and click Install Tidyverse. If you are quick, if you're quicker than me, then you just follow the notes, right? You just follow the note. Okay, it takes a little bit of time. Now, Tidyverse is a big package. If you are using your computer, you don't have to install again Tidyverse, right? Because it's already in your computer, okay? But if you are on Rstudio Cloud, then you need to install it again if you are working on a new project, okay? But if you are using your computer, once you have installed the package, you can just type library. You don't have to download and install it again. And I need to also install Broom. Broom is a small package. Okay. Okay, and now Heaven. Okay, forgot to tell you. This one I create a new project. Okay, if you remember, in the folder, kan? In the folder we did last week, I click create project. Okay, right. Heaven is also not a big project. Okay, not a big package. Okay. Okay, and the last one is here. I think no need here. Not necessary here. Okay, and after that, we are going to read data. Read data. Data is diabetes.dta, right? So we can upload the data into Rstudio Cloud. Right, and it is there. And then we use a function called read underscore DTA, okay? Read underscore DTA. And I'm gonna call this as what? Data log. Okay. In my notes, I've got this, all right? In my notes, I've got this. But since the diabetes.dta is already inside the working directory, so I don't need this. I can just delete this. Okay, diabetes.dta. Make sure the brackets are just adequate. And then you can click the green button or just press Control Enter. Right, it says could not find function read underscore DTA. Most probably because I have not run this package. Okay, I have not loaded this packages yet, so I need to go back and click this green button again. Right, now it says all these things. I think this should work now. Right, and you should see a data underscore log here. We have 3,820 observations with 19 variables. You can click here and Rstudio will show you the variables, okay? Variable names and the variable labels. F triglyceride, fasting TG, HDL is what, total cholesterol is what. Okay. What's next? We can use Glimpse to have a very quick look of our data. All right. So it says I use data.log. So I'm gonna change this to data.log. Okay. And we have 3,820 observations rows, and we've got 19 columns. And we have character variable double, which actually a numeric variable. Double and label is a numeric variable, but actually it is not, okay, because it's a double, but actually it labels something. All right. So 0 means this is DMDX is history of diabetes, okay, history of diabetes. So 0 means no diabetes and 1 means have diabetes. height, weight, waist, hip. This is the average systolic blood pressure. This is the average diastolic blood pressure, HbA1c, fasting blood sugar, modified oral glucose tolerance test at 2 hours, total cholesterol, fasting triglyceride, HDL, LDL, gender, gender 0 and 1, and C, rural, urban, and BMI. Okay, so we need to convert um, rural and gender and also diagnosis of diabetes mellitus from double or label variable to factor variables. Okay, so to do that quickly, we use these functions mutate across. Okay, across. It means that we will choose whichever label variable, which is this one, sorry, 1, 2, 3, automatically it will convert to a factor variable. Okay, to factor variables. So imagine if you have like 10 or 20 label variable, you don't have to do this 20 times. Okay, you just do once and it will convert automatically to factor variables. But again, it does not work with .csv. Okay, .csv doesn't work with .csv file. It only works with Stata, SAS, and SPSS. All right. Okay, so we can do this. Right, and we'll see what happens later, right? So we run this, okay, and then when we again call these functions, we now see that gender is now a factor variable, rural is now a factor variable, and also the MDX is a factor variable. Now it convert from 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, and 1 to no, no, and yes, female and male, rural and urban. Okay. Right. Okay, that's basically very simple data wrangling, right? And of course, you do exploratory data analysis, looking at plots before you go on. Okay, but in this case, I'm just going straight to logistic regression. Okay, so I skip the exploratory data analysis. Right. The exploratory data analysis will be in the long practical down there. Okay, here. Okay, now if you want to do logistic regressions, is easy. Last week we use LM. Okay, we use LM, but this week we just add one more word, one more alphabet. Okay, G, so it becomes GLM. Okay, and this is the dependent variable, and this is the independent variable, or this is the outcome variable, and this is the predictor variable. And for family, we specify binomial and link equal logit, and data.log, the data that we want to analyze. Okay, so and this is a symbol that we call as tilde, tilde, Okay, and I will run this code to perform generalized linear model. Since I set the parameters of binomial and link logic, this becomes logistic regression, and I will store the results as this object mod log dot age. You can put whatever name you want here, right? In this case, I'm going to name this object as mod log dot age. Okay.
So Prof, every log model memang kena ada family binomial logic tu.
Betul. Kalau tak ada family binomial logic, dia akan anggap kita buat linear regression. Okay.
Okay, Prof.
So saya akan namakan this as kita punya model ni as we will gonna name this model as mod log dot age. Okay. Right. Okay. Kalau if I don't specify, okay, a very good question. Okay, let's say if I don't specify this one, okay, I don't specify binomial a family as binomial. I run this. It still run, okay? Okay, it does not run. Okay, it does not run. Okay, sorry, it does not run because because I've changed this to a factor. Okay, I've changed this to a factor. But let's say you forgot to do that. Okay, you forgot to change this to a factor, and you leave this as 0 and 1, 0 and 1, and you run this, and you have forgotten that. Oh, actually, I have not converted this variable to a factor variable. This will return you results, okay? And the result will be a linear regression results. Okay, for example, let's say if I quickly do this as dot as integer, not sure if this works or not. Okay, right? So I got this, right? So and if I summary this thing, so give me a beta value, and it will give me, see, the Gaussian family. So Gaussian family means that you assume the distributions of dmdx is normally distributed given the independent variable age. Okay, but this is wrong because this is, even though this is 0 1 0 1, but this is not accurate because you run linear regression on a 0 and 1 data. You can do that. It is not to say wrong, but it is not accurate. Okay, not to say it's wrong, but it is not accurate. Okay, so be careful with that. That's why we have to specify family equal binomial and link logic, because there is another link which is probit. Okay, probit, probit. But it's more difficult to interpret the parameter if we use probit. For example, let's say, I run this as probit. Okay, the value is 0.02826, whereas this one is 0.05. Actually, it's the same value. Okay? If you can convert from logit to probit, from probit to logit. The way you interpret logit is we are more familiar with logit rather than with probit. Okay, if you are econometrician, then you might use probit. Right. So good questions on that. And then we can type summary mod log age. Why it doesn't run? Because I've not run this yet. Okay, I'll run that. And this is the logistic regression model that we have estimated. So this is variable age, and this is the beta, okay, the estimate. Okay, this is the beta. This is the standard error of the beta. This is the z value, which actually derive from taking this number and divide this with this. Okay, so you can, I can show you. We can prove that. Copy and then just put there. Then divide it, and you get 13.23. Okay, which is equivalent to 13.23 here. Okay, and from here, from the z value, you calculate the p-value. Okay, the p-value here is 0.2 is actually equivalent to 0.00000, okay, until 2. So you have 15 zeros before 2. Okay, so this actually equal to 2 times 10 to the power of okay, maybe I Control X and write it here. So 2e is basically is 2 times 10 to the power of minus 16 okay, right. Okay, 2 times 10 to the minus times 10 to the power of minus 16. 1, 2, 3. Okay, so so you get this value, right? And then for this is a numerical covariate. Okay, age, right? So for a categorical covariate, it's the same thing, right? It's the same thing. Just you know that the gender and C rural are basically factor variables, right? So you can just put inside inside this, this code, just put gender, right? Because this is gender, right? It's variable gender. So put variable gender here. Same thing here. Okay, family, binomial, link logic, and data law. And we can put variable name. I put here the name of the model as mod log.gen. I run this. And then when I want to see this, the results, I just type summary mod log.gen. Okay. Or even I want to see a more beautiful result, a more organized one, I can use tidy mod log.gen. So it gives you a nice table, okay? Nice table here. So this is the estimate. This is the beta, right? This is the beta. And so the beta in logistic regression is log odds. Okay, so this is the log odds, and this is for male. It means that the log odds to have diabetes mellitus for male is 0.22 compared to female, whereas for age, okay, if age is increased by 1 year, then the log odds, okay, then the log odds to have diabetes mellitus increase by 0.051. Okay, so you have to be very good at interpretation now. Be very comfortable with the interpretations of the parameters. In multivariable analysis, where you have 2 or more covariates, the same thing, you just for example, you want to have age and gender. Okay, oops, doesn't work. Okay, multi-variable model. Okay, now you want to include age and gender. Okay, age and gender, and you want to name this model as what? Mod age gen. Okay, if I run this, okay, like this, I get the results, but I'm not saving this result. Okay, I'm not saving this model, so that's why I need to put something, a name there. So this become the object, okay, and then you will see this object in this environment here. For now, it is not there. Okay, it is not there yet. But once I run this, you see this is visible here, mod log.age.age.chen. So this contain the results of the logistic regression model for this object. So this is a multivariable model. If I want to see the result, I can use summary. Mod log age chen. Or if I want a more organized result, I can use tidy. Okay. So this is the estimate. You know that this is the log odds, standard error, statistics, and p-value. So in this multivariable model, if you adjust variable age, then if you adjust variable gender, then if age increased by 1 year, the log odds will increase by 0.05. The log odds for what? The log odds to have diabetes mellitus. If you are male, and you control the variable age, then the log odds to have diabetes is 0.14 compared to female. Okay. The p-value for gender is 2.02 times 10 to the power of 0.1. So it means that 0.02. Okay. So the p-value for gender is is 0, 0 point. Okay, I'll write that as 2.017 times 10 to the power of -1. Okay. So this one, okay? 2017 times 10 to the power of -1, which is actually equivalent with 0.202. Okay, which is not significant, right? And however, for age, it is 2.634, this one, times 10 to the minus of 39, okay? 39, right? So which is, like, which is, easier to write just as less than 0.001, okay? Right. Okay, what else? All right, interaction, okay? Interaction. Interaction is also easy. For example, if you want to see the interaction between age and gender, okay. So this is interaction, and I put our code chunk, which actually you can click here if you want to. Okay, and this is the interaction between age and gender. So I have covariate age, I have covariate gender, I have covariate age times gender. So there is a colon here, okay? A colon, COLON, okay? Colon. And then, and I'm gonna name this as what? A model named mod log age gen IA, okay? Puts a name that, easy for you to understand, okay? Run this, okay? Got the results very quick and right, tidy and mod log age gen IA, okay? So this should be the same with this one, okay? Right, so age, gender, and age, gender, and age times gender. This one, you can't interpret as, you can't simply interpret that, okay, if age increased by 1 year, then the log odds for diabetes increased by 0.05. Sorry. Can't, wrong. It's wrong, okay? And you can't say that, okay, if you are a male, then the log odds to have diabetes is now minus 0.347. Wrong. Why it is wrong? Because you have interaction here. Okay, you have interaction here. So in my notes, okay, in logistic regression notes, I think I have put some paragraphs on how to interpret interaction in your model. Okay, what else? Inference. Okay, inference is yep.
If the interaction is not significant, should we interpret in the model?
First, number one, you have to set what do you mean by significant. Okay, you can set a significant as 0.05, or you can significant as 0.1, or you can set a significant as 0.01. Okay, 0.01, 0.05, or 0.1. So when you say it's significant, what would be the cutoff value? So that's you have to decide as a researcher. That's number one. Number two, whether it is significant or not, it also depends on the magnitude of the interaction, not the p-value. If you know that if the sample size is huge, even a non-meaningful difference will be significant. Okay, and you know that if your sample size is small, even a big difference will look as if not meaningful. Okay, or not significant. So I think you have to look at two aspects. Number one is the p-value itself. What do you set for your study? And number two, what would be the significant value of the interaction in terms of clinical significance? So you have to look at the clinical significance and you have to look at the statistical significance. You have to set both very clearly in your methods. Okay. Right. So for inference, you know that for inference you look at the p-value. You also look at the 95% confidence intervals. And to do that, it's quite easy. Just add. We got a p-value already right here, kan? And to get, but however, you don't see 95% confidence interval here. So where are they? Okay, where are they? To see that you can, there are ways to do that here, but I think the easiest one would be just to use tidy function from Broom package and then just type conf.int equal true. Okay. So this is inference. Okay. And which model do you want to look for? So remember we have we got mod log gen, mod log ish, mod log ish gen IA. So all the models are here, right? So which model you want to look at, and then put confidence interval true, and then you get this confidence low and confidence high. The default is 95% confidence interval. Of course, you can change this to 99% or 50% confidence interval, but always we just accept at 95% confidence interval. So it means that in a model where you adjust gender, if age increased by 1 year, then in a large sample, the log odds could be as low as 0.043 or could be as high as 0.058. In a model where you adjust a variable age, male populations have the log odds of or the log odds as low as minus 0.07 or as big as 0.342 to have diabetes mellitus. Okay. Okay, and remember, this is the log odds, okay? This is the log odds. And if you use SPSS, you can just click something, right? I think you can click exponentiations of B, and SPSS will return both the log odds and the odds ratio values. In R, there are many ways to do that. One way is to use the same function here, but just add one more parameter, which is the exponent. Okay, by right it should come out exponentiate. Okay, if you are using your computer, the not the autocorrect, the auto filling something, it will come out, but this one, exponentiate. True, make sure you got comma there. So this is the odds ratio. So you can confirm this by, just tidy, and you can exponentiate this thing. Exponentiate, Control V, and let's exponentiate beta for gender 2. So you got 1.05 and 1.14, which is the same as 1.05, 1.14. Okay. Right. What else? Prediction. You can do a few types of prediction, but maybe for your level, you if you know two of them are good enough lah. Okay, one is to predict the log odds, and the other one is to predict the probability. Okay, so I use augment. Augment also comes from package, from a Broom package. Okay, copy, and then predict. And what I want to predict, okay, I want to predict based on mod log age gen, this one. Okay, so you can predict other model too, right? So for example, you want to predict this one, IA, put IA there. Let's say you want to predict for model gender only, right? You can do this. So this is the prediction for a model with age and gender. This is also the prediction for the log odds, predicted log odds for age and gender, but with interaction. And this is the predicted log odds for gender only. Okay. What about age? Okay. Age. Yep, we got more log age there. So this is the predicted log odds for a model with age only. So you see that age. So it means that if this person or in a population age all age 70, then this is the log odds to have the diabetes mellitus. If in a population with 20 years old, then this is the log odds to have diabetes. In a populations of 29 years old, this is the log odds to have diabetes. Right. So this is predicting the log odds. If you want to predict the probability, then very easy. Just change this to response. Okay. Response. response. Okay. So now this is the predicted probability. So if you have a populations of 70 years old, everyone is 70 years old, and all female. Okay, this is a variable in a model with age and gender. So all in that population, everyone is female, and everyone is 70 years old. 24.6% will have diabetes mellitus. Okay, 24.6% of them will have diabetes mellitus. In the populations where everyone is male and everyone is 20 years old, all those male are basically 20 years old, then 2.7% will have diabetes mellitus. Okay, will have diabetes mellitus. Right. So, okay. So this is for if there is interaction. This is for a population with female only. Okay, that's why when you have female, you have equal probability. Okay, so in a population where you have all female, 11% will have diabetes. In a population where you have all male, 13.5% will have diabetes. Okay, what else? This is the evidence or the proof how to calculate that. All right. Once in a while, I do ask this question. Okay. So to get the odds, what you need to do, you have to exponentiate, right? You have to exponentiate the log odds. So this is the intercept here. So beta 0 plus beta 0 plus beta 1 x1 plus beta 2 x2. All right. So this is beta 0. Okay. Let us copy this one. Okay. So this is manual calculation. So beta 0 plus beta 1 x1 beta 0 plus beta 1 x 1 plus beta 2 x2, right? Okay, this one, right? Which actually is the same as, which actually the same as the intercept plus beta 1, which is what? Beta 1 is the, this is the model for 46467, which I took from this one. Okay, model age and gen. Okay, age and gen. So this one is age, and this is gender. Okay, gender. Right. beta 1 is okay, H1 and beta 2 gender. Okay, ish. All right, okay. So so this gender basically is male. Okay, if you look here, it's male. Okay, it's male. So intercept plus beta 1 H1 beta 2 gender male. Okay, so for this one, the first observations. Okay, the first observations is gen this one. Okay. 4.67, which is this one. Sorry, this one, 4.67, 0.05. And what is the age for observation number one? Observation number one, the age is 70. So age is 70. And then the gender is female. Okay, so that's why it's become zero. It becomes zero. Okay, so that's the odds. So the odds is 0.32, and the probability is basically the odds divide by 1 plus odds 1, which is 24.6%, which is this where is it? Okay, 24.58. Okay, just the difference, a decimal point. Okay, okay, the same. Okay, let me enlarge this. 24588, 24588. Okay, right. Okay, what else? Second observation is like this, right? So yeah, that's basically the flow of doing logistic regression analysis. In the long practicals, I go, same flow, but a little bit more elaborate, from reading data, viewing your data, describing your data, and then do some transformation, do some data explorations, then estimate, making inference. Then this is model selections. Okay, model selections. What else? And I got one important thing in model selections, which is ANOVA. Okay, likelihood ratio test. It should be here. Prediction, model checking. This one, linearity in logic, is something that is important. But for you, okay, for multivariable analysis course, no need. Okay, no need. This one only for the one that's going to do for EPIC group. Okay, later. Okay. What else? And this is the diagnostic plots, or the model assessment. How to do model assessment. Okay. If you can do all this, kan, definitely you got 100% marks lah. Okay. If you know how to interpret, if you know how to do logistic regression and you know how to interpret, then you got 50 marks. If you know how to, when I say interpret up to interaction lah. Okay. If you know how to to do everything, you got 100%. If you know how to interpret results and make from a nice table, you format the table nicely, you get 50 or 60 marks. And in between too, you know, if you can do predictions and if you can do model selections, and things like that. So I think what I'm gonna do is, you know, I will leave you to continue with the long practicals. I'll come back at 12:30. Okay, I'll stop the WebEx at 11:30, and I'll come back at 12:30 to answer your questions. Okay, you do the long practicals. If you face any problems, you can discuss at 12:30. All right. Is that all right? Is that okay?
Okay, Prof.
Try first.
Prof, sorry,
Excellent. Yeah.
Prof, yang ada prediction punya site tadi, actually we use type dot predict to link and response kan? What's the difference between these two, Prof? Link dengan response.
Link akan bagi the log odds. It means that if you this one for mod log age and gen, this value is the value. Okay, first kita tengok age and gen, which is this one, 4.67 plus 0.05 times 70 plus 0.135 times 0 because they're female kat sini. So, tak apa nanti kita tunjuk So we got this this one. Okay, this one minus 1.12, okay? Minus 1.12, which is this one. See? Minus 1.12.
Function
Datang
link
daripada
kan?
Yes, function link, which is this one kan logistic regression equation is beta 0 plus beta 1 x1 plus beta 2 x2, right? So this is the log odds, and to get the odds you need to exponentiate the log odds. Okay,
Akan jadi
log
ratio
odds.
kan, Prof kan?
Odds ratio lain. Odds ratio is exponentiate the log odds, and odds ratio is the odds. Okay, for example, this one use odds 1 kan, so you take for log odds 1, and then you calculate another one. For example, okay, copy this one, and then we take this one, which is log odds 2, and so odds ratio is the ketika odds ratio 1 versus 2. So this is odds 1 versus divided by odds 2. Okay, so for example, of course, if you want to get the odds ratio, you can automatically exponentiate this one, and you get that this one odds ratio. Okay, odds ratio. This is odds ratio. But when you calculate manually, it will be different. Okay, it will be different because you have to get the odds for each of the person. So the odds of this guy compared to the odds of this guy, you get the odds ratio of this over this. Okay. Tapi nanti a bit complicated sikit tu. Bukan complicated, maybe susah sikit nak graph sebabnya your masa MPH, you just stop here. Masa dekat MPH, you stop here, okay? Masa MPH, you stop here, and then you interpret, okay, this is the odds ratio. If the age is 1 year older, then the odds ratio to get diabetes is 5% higher. If you are male, then the odds ratio to have diabetes is 14% compared to female. But now we have gone one more step, that is to look at the predicted value and use that to calculate the log odds, the odds ratio, and the probability. Okay. Dekat MPH you stop dekat sini saja. Tapi bila you stop dekat sini, the dangerous thing is that if you have interaction, okay, if you have interaction, macam mana you nak interpret? Because kalau you cakap, okay, if age increase by 1 year, then the log odds, okay, this one is log odds. Log odds increase by 0.04. If your gender is male, then your log odds is minus 0.34. It is wrong because this is interaction here. So to do that, you have to go to this and calculate the log odds for the model with interaction. For example, this one. Okay, this is the interaction. So this is the log odds for the this is probability for the population of this one and this one. This is this for 20 years old and male, 29 years old and female. Think about it. Okay, think about it. I know that it's quite difficult to digest this in this, very quickly, or very quickly now. So take your time to see the benefit of doing this when your model has interaction. Okay, what else? Okay lah. So I think I've stopped there. And nanti pukul 12.30 kita datang balik.